for our live seminar. It is my pleasure to introduce Behzad Tahmasebzadeh. He is currently a postdoc at University of Michigan, but prior to that, he completed his bachelor's and master's in Iran, and he completed his PhD at the Shanghai Astronomical Observatory before joining University of Michigan, primarily working with monumental derive. And he's really an expert on the dynamical modeling of all types of galaxies. And so I think that's what he's going to talk to us about today. So take it away.
Thank you for introduction. Thank you everyone for coming. And it's my pleasure to be here, and thank you for opportunity. So today I will talk about our ongoing project about constraining the black hole mass in low mass galaxies using JWST NIRSpec IFU in low mass regime. So I will start with briefly talk about the different scenario for formation of black hole seed, and say why it's important for us to constrain and catch the black hole in low mass galaxies and what we are looking for. So there are three main well-known scenario for formation of supermassive black hole seed at early universe. The first scenario is basically gravitational runaway, which is actually is like at the early universe, in some stellar clusters that they were very dense and massive. A few stars can collide together, can get close very much together, and by colliding and merging form massive stars, and that massive star can basically collapse and form a black hole. And in another scenario is a stellar in population tree stars. It's basically mentioned that the very early stars at the beginning, they are massive enough, a single star, they are massive enough that collapse and form a black hole, basically like a stellar black hole. So these kind of black holes, they are tiny at the beginning, so they need time to grow, and so we expect it to be these black holes be less massive, for example, than gravitational runaway. Another scenario is direct collapse. Basically means that at the early time, a giant and very massive cloud of gas directly collapse, and without forming a star, directly will collapse into its own gravity and form a black hole without forming a star, basically. And this scenario, the direct collapse, will lead to a more massive black hole. So each of these scenarios predict different observation. For example, on the population tree stars, the number of the low mass galaxy, the number of the low mass black holes around us will be much more than, for example, what direct collapse predict. And under direct collapse, for example, scenario, the number of the supermassive black holes should be more than the intermediate mass black holes here. So as we go to the lower mass galaxies, we will have, under direct collapse scenario, we will have more massive black holes. And for example, under population tree star, we will have the lower massive black holes. If you see here, when we are in higher mass regime, galaxy regime, these models like overlap. But when we go toward the lower mass galaxy regime, the prediction of these models distinguished. So we need to push the limits, go toward the low mass galaxies, and try to find the black holes and constrain the black holes. And the point is, up to date, there are a few, maybe less than 10 massive black holes are found in the low mass galaxies mainly. And the main challenge is observation, because when we go to the lower region of the black holes, the velocity dispersion is very low, and it will be hard for many instruments to catch that resolution. So here I list 3 examples of the low mass galaxies that we can search for black hole. The first is all ultra compact dwarf galaxies, we call UCDs, or compact ellipticals and nuclear star clusters. There are different scenario formation pathway for these. For example, for UCD, some believe that these kind of systems here, a very small and tiny system, they are just bright and massive Grover clusters. But there are another narrative that mention these kind of UCDs are basically the nuclear remnants of the previously dwarf galaxy, which is stripped away when it's rotating around the host. And the outer part of this galaxy is stripped away because of the tidal effect. And also for compact elliptical, the same story is here. So these compact elliptical can be formed through the tidal effect. For example, they can lose the majority of their mass, and only the central part, the core, will be remain because of the strong gravitational bond. And another scenario is probably these kind of compact ellipticals, they form by merging of a few Gruber clusters. But there is a point. If these are formed by Gruber clusters, probably they are not host the supermassive black holes. The supermassive black holes are centered to the galaxy by merging when a few bigger galaxies merge. So we will have the supermassive black hole or massive black hole in the center. So if these are formed by, for example, or if this is a Gruber cluster or formed by Gruber clusters, we are not expected to find any black holes in the center of them. So here is a simulation. If I that can show, for example, if this is a previous dwarf galaxy, how with rotating around the galaxy host, the outer part of the stars that they are less bound to the to its self-gravity will be stripped away, and by after a few rotation or a dynamical time period, it will be only the very central part will remain. And so we expected that if it's host a black hole, it should be a massive black hole as well. If it was a dwarf galaxy, for example, then if the intermediate mass black hole are supposed to be in, for example, in some Gruber clusters. But if it's like the previously dwarf galaxy, it should also contain a massive black hole. So here is our sample. We have 18 targets, and we got the data from JWST in the first cycle, and still we are modeling it because for a year we were dealing with some data reduction and cleaning the data. And this is our sample. The stars here, this is the effective radius of our sample, and this one is the stellar mass. So our samples contain nuclear star cluster, UCD, and compact elliptical. The mass of the galaxies are from 10 to 7 to 10 to 9 solar mass, and the effective radius is from like 10 parsec to a few kiloparsec. And we will use dynamical modeling code called Forstand to constrain the black hole masses. So I briefly describe how we make a dynamical model and how we constrain the black hole. What we have from observation is a photometric image. This is just a typical example. It's not a UCD. It's just a typical example from Vanden Bosch 2008 to describe this modeling procedure. So from the observation, we have photometric image. And from the spectroscopy, we can extract the kinematic data. So when we extract the kinematic data, this is a mean line of sight velocity at each aperture here, and velocity dispersion H3 and H4. The H3 and H4 basically means how the line of sight velocity distribution at each beam is deviated from the perfect Gaussian. For H3, for example, it means like the skewness, and for H4, it means how it is so flat, it is flat, or it's peaky, the line of sight velocity distribution. So once from the photometric image, we try to fit some 2D surface brightness and then deproject it to a 3D density by some assumption. At this stage, we consider some assumption, for example, the viewing angles. And then when we have the 3D density of these galaxy with the deprojected 3D density, we can make the gravitational potential of the stars and add other component of the potential, like dark matter, black hole, and whatever you want. And all your free parameters will be there. So you assume different potential for a star, dark matter, and black hole. You have some free parameters here. And then you try to integrate like thousands of the orbits. We need to make sure we reproduce all different kinds of the orbits. When we reproduce the initial condition, for example, the boxy orbits, the warm orbits, and the cold circular orbits. And then we superpose all the orbits together, similar to the aperture that as we have in the kinematics. And when we did that, we try to, by superposing these orbits, we give the weight to each of the orbit and adjust these weight until they can reproduce our target density. Here, for example, this is each orbit, and this is like our discretized density. And by summing of all the contribution of all these orbits at each cell with given a weight, we can reproduce this target density to make sure our model is self-consistent. We do the same with the kinematic information. So for example, this is the kinematic data for the observed kinematic data. They have a line of sight velocity distribution, and each orbit has different like line of sight velocity profile. By giving them different weights and playing with these weights during optimization, we will finally to reproduce the target line of sight velocity distribution. And by reproducing this process like thousands of the times, with giving different black hole mass, different dark matter, we finally ended up with a best fit model that can reproduce the main features in line of sight velocity, velocity dispersion, and higher kinematic moment. And at this moment, we are able to constrain to, for example, black hole mass, whatever we consider in a stellar profile, for example, the inclination angle, and etc. So before applying our method to these compact ellipticals and compact galaxies in JWST, we need to validate our method to see how powerful is our method when we apply to these compact elliptical in Virgo cluster. So what we did, first we create some n-body simulation, n-body representation of these compact stellar system, like the compact ellipticals and UCDs. And then we put this n-body simulation in this Mock galaxy at the distance of the Virgo cluster. And we try to reproduce some kinematic map with a similar resolution as JWST. And we give them, we locate different black holes. So for example, this is the output of our model. This is mass to light ratio. And this one, this x-axis is the black hole mass. The contours are the 1 sigma profile, 2 sigma, and 3 sigma of the best fit model. The blue contours are isotropic Mach model, and the red one are anisotropic. This column, the black hole are the black hole in this system are 10%. It means that 10% of the stellar system is itself a black hole. And here is 1%, and here is like 0.1%. These gray horizontal, these gray lines are the true value. So for example, here, we see the best fit of the model can recover the true value of the black hole. We know the true value of the black hole. They are just the Mach model. So we conclude that as long as the black hole in this system are like 1% of the total stellar mass above, we can recover the black hole mass accurately. But however, when the black hole gets like less than 1%, we cannot recover because, of course, the stellar influence of the black hole is much smaller than JWST resolution. So we apply to the observation. This is our first target, the UCD 736. It is in the located between 3 giant galaxies and in the Virgo cluster. So by fitting some spectral template to the spectra that we have from the stellar spectrum that we have from JWST, we can extract the kinematic information. That Solveig is a PhD student in University of Calgary. She extracts the kinematic information for us, and then we run our model based on this kinematic information. So this UCD is extremely small. The effective radius of this UCD is only 14%. This is really small. And if you see the blue one here, the blue UCDs, there are 3 other blue UCDs here. They are those UCDs that previously find a black hole in them. Then the black hole is around 10% of their stellar mass. But the difference is these UCDs are extremely close to these hosts. So make it like more possible that they are under tidal effect and, or strip nuclei. However, this UCD is right between, it's not gravitationally bound to any of these hosts. So what we found, the orbit, like using orbit Schwarzschild modeling, we found around, we detect a black hole mass up to 3 sigma level here, 1 sigma, 2, we detect a black hole mass. And it's around, the black hole here is around 2.2 times 10 to 6 solar mass, which is around 10% of the stellar mass of this UCD. So basically 10% of the UCD is only the black hole. We also used other methods like Jeans anisotropic modeling and distribution function modeling. However, they didn't provide the lower limit because they are not using the high velocity moment as efficient as the what's Schwarzschild model, Schwarzschild technique using. So this is the line of velocity dispersion profile for the best fit model. And this line is a model without a black hole. Here is the H4 profile, and we can see that the Schwarzschild model can nicely match the observation. So if we compare this UCD with this is the 6, like previously, only in 5 other UCDs, the black hole was strongly detected. And this one is the 6th UCD that we could find the black hole. However, this UCD is the faintest and the smallest UCD that is observed today. And also, when we compare the black hole ones, it's also the least massive black hole compared to others, the UCDs that's a black hole is detected. So one interesting thing that we were computing to see what is the tidal radius of these, for example, this UCD, and also the tidal radius of these giant massive galaxies. And the tidal radius of this UCD is around 10% larger than its optic radius, like around 1.4 kiloparsec. And the distance to this M59, the nearest or the closest massive black hole, massive galaxy, it's around 106 kpc. However, the tidal radius of this galaxy is 110. So which means this UCD is not under tidal effect of any of these giant galaxies. So the idea, one possibility is this UCD is on an eccentric orbit and go toward the center, probably before it's passed toward the center of the Virgo cluster and heavily stripped away the outer part of this UCD. So this is the only possibility because, it's not, or maybe one of the possibility that's because it's heavily stripped away. So probably it's like being in an eccentric orbit and went through the close to the center of the cluster, and now it's only remained by a stellar shell around a stellar system with around 1.4 tidal radius. So the second object, this is almost ready to submission for this target. The second target that we are working now is a compact elliptical right in the center of the Virgo cluster. So this compact elliptical is right here in the center of the Virgo cluster, and it is a companion of the giant M87 galaxy. So the effective radius of this compact elliptical is 0.5 kpc, and the mass is around 10 to 9 solar mass. The interesting features about this galaxy is it has a double nuclei in the center. So in Cormendi et al. 1997, they tried to model this galaxy using the anisotropic modeling, and they found that when they use isotropic Jeans model, they could predict a black hole by 6 times to 10 to 8 solar mass, which is around 10% of the stellar mass of the galaxy. But they found if they use anisotropic Jeans model, they cannot predict any black holes. So a model with 0 black hole can easily fit the data. So isotropic Jeans model, they could predict the black hole, but anisotropic, they couldn't. So the black hole was not confirmed, but the idea was if there is a black hole, 10 to 8, so 6 times 10 to 8 black hole, from M sigma relation, this galaxy is an outlier from both M sigma relation and also the bulk mass and the black hole mass. So it also indicates that this galaxy could strip, stripped away previously because it has very high velocity dispersion. So previously, it was a giant galaxy, and that include this massive black hole and with such a high velocity dispersion. So they tried to say, in this paper, they said some scenario for forming this double nuclei. One of the idea is probably they are some stellar clusters that they are infalling because of dynamical friction. But this scenario need a it can happen in very short time, like less than, it's a few mega year. So it's not a long-lived actually system, considering this is a very old, like the galaxy. When you look at the stellar population, it's very old galaxy. And the color difference between these two peaks is similar. So probably, they cannot be two different stellar clusters. Another scenario, which is stronger, is eccentric disk. That's probably they are the eccentric disk in some viewing angles that we can see the stars when they are moving in like apocenter, they are moving slower than the precenter, so they can make a brighter peak and a fainter peak. So before going toward the modeling of this system, let's take a look to some simulation and theoretical work that is done by Anne Maria group. So basically, one of the formation scenario for these eccentric disk is when we have circular orbits around the supermassive black holes. By merging the disk, if there is a binary black hole and it's merging together, they can emit a gravitational wave. And if the gravitational wave is asymmetry, it will lead supermassive black hole get a recoil kick. And by getting this kick, it will affect that some orbits, some stars that they are rotating in a circular orbit, they will get like go to eccentric orbit because their velocity will get affected in the frame of the supermassive black hole. And another dynamical signature that we can find if this is the case for the formation of the eccentric disk, that is there, if it happen in the system, depends on the radius of these, depend on the position and the radius and the velocity, the circular velocity of these stars, and relative to the kick velocity of the black hole mass, these stars either can keep rotating on a prograde orbit like the thing here, or they will get retrograde on the retrograde orbit like the dashed lines here. So this is like the dynamical effect of the formation of the recoil kick. If this eccentric disk in this compact elliptical is formed by recoil kick, so we expected to find some retrograde orbits around in the region of the eccentric disk. And also in another studies, they examined like different scenario with different velocity kick for a black hole similar to M31, and find that it's likely 50%, a large fraction of the orbits around in these eccentric disks, they are counter-rotating orbits. And as they go to the outer region of the eccentric disk, the fraction of these counter-rotating will be increased. So, sorry, I didn't say this axis. This is like the z-axis of angular momentum normalized by the circular of the normalized by angular momentum in a circular orbit at the same radius. So we see the positive one, they are prograde orbits. Here are the negative, that they are retrograde orbits. And as we go toward the outer region of the eccentric disk, the fraction of the retrograde orbit will increase. They have another study a few years ago about the kinematic prediction of these eccentric disks. And it's interesting that if we look at these eccentric disks at different viewing angles, for example, along the major axis, end-on view, or face-on view, or edge-on view, we will see different kinematic features and different photometry. For example, when we look at it at the end-on view, we will see only one, it's like one core stellar system. However, we have in a face-on, we have a bright core and fainter core. And when we look at it as an edge-on view, we will have two core which are almost symmetry, or at least not significantly different rather than this. And also the velocity dispersion and the line of sight velocity. So let's take a look at what we have from JWST, what the kinematic that we extract. This is the HST image for this galaxy. We applied some unsharp masking to the center of this galaxy, and it's clearly revealed these two double nucleus in the center. So we have the faint peak and the brighter peak here. And when we compare with the kinematic that we got from the JWST, so the peak of the velocity dispersion is clearly off-center from the kinematic center of this galaxy. So this is line of sight velocity, this is velocity dispersion. Here is the kinematic center, and this is the velocity dispersion, which is clearly off-center. And when we compare it to the photometry, we can see that the peak of the velocity dispersion is around the fainter peak, which is possibly the location of the black hole. The location of the supermassive black hole is always in the center of the velocity dispersion peak. When we have a single velocity dispersion, I mean the peak of the velocity dispersion. So when we compare it with the data that Corman et al. Use in CFHT data, there are some mismatch with their data and our data here. However, they have lower mean line of sight velocity distribution and higher velocity dispersion. Oops. Higher velocity dispersion. That is still we didn't understand what's the reason of this matching. Probably it's because of the PSF, but JWST predict the higher mean line of sight velocity and lower velocity dispersion in outer region. However, in our dynamical modeling, I use the JWST, the black here, the black dots here, and for outer region, I use the CFHST data to constrain that, to be able, if there is a dark matter, we need the data to the outer region to be able to constrain the dark matter, because the dark matter effect in the very central region is minor, so we cannot really constrain the dark matter with the kinematic only in the region. So I remove this data here, the red data here, only use the black, and for outer region I use this older data. So before going to the model, let's compare these kinematic and photometric that we have with some of the simulations. And we found, interestingly, that only eccentric disks that we are looking at in the face-on view, that they can reproduce these features that we have here. First of all, the black hole is in the fainter peak location. It's in the central velocity dispersion, exactly what's happening here. And the location of the black hole is not in the zero line of sight velocity region, or we call it the center of the kinematic map. So we can see the black hole is here, similar to the simulation. So we conclude if there is a black eccentric disk in this system, it's a face-on. It's in the face-on view compared to this simulation. So let's move forward, and I will present our dynamical models for this. So for orbit superposition dynamical modeling, the first things that we consider is applying some symmetry, some symmetry in the modeling. And it is a self-consistent model. And in a steady state, what eccentric this has none of them. It's not symmetry, not a steady state, and not self-consistent. So making a superposition model to exactly map eccentric this is extremely difficult. It takes a long time. It's in our to-do list, but it's really difficult. But even if you are able to do that, there are some serious questions to ask. First of all, eccentric disks are not in equilibrium. When we want to make an orbit superposition, the first assumption is the equilibrium. And then for making the orbit superposition model, we need to have a black hole and disk that remain stationary in a rotating frame. And it's hard. It's even a question, do we have such equilibrium in a real world? And how these materials can affect the dynamics. So for example, if the mass of the disk is around 10% of the mass of the black hole. So there is a mass there, so it can also affect the orbits. And also it would be very difficult because not only we have lots of parameters, viewing angles, the pattern speed, or the bulge properties. So it will make this computational modeling really expensive. And another thing is, when we have like this kind of kinematic map, these map is not only for eccentric disk. They are also the contribution of the stars in the bulge, that they are not in part of the eccentric disk. So how we distinguish the eccentric disk from the kinematic of the bulge or the other background stars, like for example, in the other side. So there are still some challenge. So we applied our modeling without, we just make some axisymmetric assumption for modeling. We reproduce we make some axisymmetric potential and try to fit the data. So this is the data, and this is our model. Still, it can produce many features in the kinematics. And this is the line of sight velocity. We also try two other approach. The first one is we try to mask the high velocity peak of the velocity dispersion. So we aim that this model will give us the minimum required black hole mass in this system. And in another scenario, very naively and even foolishly, we push the peak of the velocity dispersion to be center. So we expect that this model can give us the maximum possible black hole mass in the system. So this is the data. This is the output of the model. This is the mass of the black hole under different model with spherical Jeans modeling, or considering the dark matter, and also the masked and also shifted sigma. And this model is from the result here from Corman et al. These four here are from Jeans modeling, and here is our Schwarzschild modeling. So we can see that many of our Schwarzschild modeling here are pretty consistent with what Corman et al. Reported. However, we are not reporting an exact number of the black hole. It's not possible. But first of all of our model, until 3 sigma confirm there is a black hole. So we don't have the zero mass black hole that can fit the data. All of our model up to 3 sigma level strongly predict the black hole. So there is a black hole there. We conclude that the black hole could be anything between 4 to 7 times 10 to 8, which is 5 to 15% of the stellar mass in this galaxy. So now we have our orbital. We can take a look at the orbital structure of our base fit model, right? We have a bunch of orbits. We know the weight of the orbits, and we can take a look at the internal structure. Here we plot the orbits phase space. Each dot represents one orbit, and the size of each dot is the weight of each orbit. And the color is eccentricity. This column is the circularity, angular momentum normalized by circular angular momentum in a circular orbit. And here is the radius. The dashed line here is our JWST kinematic extent here. And this dashed line here is around this eccentric disk region that we can see from the photometry. So when we look at the simulation from Bright and Akiba, for example, we can see if, because of the recoil kick, they will make some orbits to be retrograde, and the fraction of the retrograde orbit will be decreasing and reach to 50% by the radius. So, for example, this is a model that all orbits are purely circular, and this is a model that's the orbits. The initial orbits are initially eccentric in eccentric orbits. They are not less circular, not circular. But anyway, in both of them, we will see at some point the fraction of the retrograde orbit will be reached to 50. So when we look at the orbital structure model, we see in the region of the eccentric disk, the fraction of the retrograde orbit. So these are retrograde orbit, these are prograde orbit. And the red one here is the fraction of the retrograde orbit. We can see it will reach to 50% when we reach to the outer region of this eccentric disk. And it's kind of increasing, similar what they have here. So it's basically, it's exciting. We don't want to claim, well, we dynamically find the signature of the eccentric disk, but there is some retrograde orbit needed to reproduce this kinematic map. Yes.
So yeah, oh, I guess I can look it up there. So that's where the first dash line, the vertical dash line, that's where you, it's like at 12 parsecs?
Yes, 12 parsecs.
Okay,
yes.
got it. Thanks.
So the fraction of the retrograde orbit is clearly decreasing, which means that, you know, for reconstructing this kinematic, we really do need the retrograde orbit. How real they are, because we are applying the axisymmetry, it's another matter. We will apply some, so what we have planned to do now is try to see how we can match some embodied simulation to these kinematics, and also if we could make the orbit superposition. But by now, we can conclude a few things about this galaxy, that first of all, if there is eccentric disk, it's probably is in a face-on view. We clearly catch the large fraction of retrograde orbits in this eccentric disk region, which is consistent with the simulation. And we confirm up to sigma level, 3 sigma level, there is a black hole there. So if we take a look at the scaling relationship of the black holes, that the mass of the house and the mass of the black holes here. So here the region, as we can see here, when we go to the lower mass region, we don't have enough data. You know, we don't have enough, like it's less than 10. That's up to date, robustly constrained. And these two of our models that we model up to now, up to date, they are like around 10%. The mass of the black hole is around 10% of the stellar mass, and they are clearly consistent with the direct collapse scenario that I described at the early time. So of course, we need a lot more sample. We need to finish all our sample to make here, you know, to have enough robust sample to fit some scaling relationship. But the idea is if we find more and more overmassive black holes, then the direct collapse scenario will get more like weighted compared to the other scenario. So yeah, I would stop here.
I was curious, what kind of dark matter profiles are typically used for these ultra compact objects?
That's a great question, and I forgot to talk about it. So, for example, for this one that we have the dark matter, we add a NFW profile. So, however, the point is we couldn't catch any dark matter. So, in any of we had two models up to now. We put it in NFW, but like we couldn't like constrain the mass of the dark matter. Actually, basically, even without the dark matter, the data would be nicely like reproduced. So we couldn't constrain the black hole, even for this system that I use the kinematic on up to the outer region. So we couldn't constrain any dark matter. So we think there is no dark matter there, which is consistent with the simulation, because when it's start to strip away the outer part, the dark matter particles are those that stripped away at the first place, based on the simulation. Because they are less bound to the galaxy center, right? They are gravitationally less bound. So they will be stripped away in the first place. So in both of these systems, we didn't find any dark matter. And it's actually also consistent with this overmassive black hole and this narrative that these like galaxies, they are stripped away. They are, I mean, the nucleus, a stripped nucleus, rather than like Virgo Cluster merging or something like that. But yeah, we didn't find any dark matter. That's a good question. That's a point. For example, they say, okay, what kind of NFW? Is it like Cosby or core? We tried with both of them, but we couldn't constrain any dark matter. It seems they really, they don't have dark matter, or they stripped away, yeah, based on this kind of simulation.
The UCD like 7431, that's really out in the tidal radius. Is it possible at all that it could have formed like outside of a massive galaxy, like in some residual like low gas region, and maybe that could also be related to the
absolutely, yeah. It depends in the very early stage of the merging and formation process. It could form there and then just didn't bound to any massive galaxy because of the high velocity. Exactly, yeah. So it's, you know, this shows that we don't necessarily need to be very close to the giant massive galaxy that like the outer part is stripped away. So even if it's not bound to any galaxy, but they have like this high velocity and eccentric orbit compared to the total cluster, it can undergo this stripping process.
Were these previous 5 UCBs studied in a similar way? Like, was the modeling similar, or did it done in a very different way?
Yeah, Schwarzschild modeling and Jeans modeling. Yeah, they robustly constrain there. Yes.
I have many questions, but my first one on this would be, if you're trying to look at the like formation of supermassive black holes in the early universe, and whether or not massive black hole seeds or top 3, something like that, would you want to target galaxies that have had a more uncomplicated history, that started maybe low mass and continued growing just very slowly, rather than targeting galaxies where you're not sure, say like grew to like Andromeda size and were massive, and then we're just completely stripped away at the outset? Like, isn't it the mass of the galaxy and the mass of the black hole, and if the mass of the galaxy keeps getting messed up because of tidal stripping, that makes that measurement very
So,
difficult.
we need to go to low mass galaxies. This is the things that we need to know. So most of the low mass galaxies, they are in a complicated environment. It's really hard to find the low mass galaxies in like the void or in the field. It's not impossible, but it's like raw, but I mean rare. That's an idea. We can focus on those systems as well, but most of the low mass galaxies I basically will find on clusters environment. It's rare to be away on like and probably they don't, they didn't also have a merger, probably they didn't have the supermassive black hole as well, or the black hole didn't have chance to grow or something like that. But yeah, the low mass galaxies basically are in the more complicated environment. But that's a good question. We should write some proposal at some point for some low mass galaxy in the field, right?
I mean, the mass galaxies. It's just that you say it back to me, I'm like, yeah, I don't.
Yeah,
I have a suggestion. I just have criticism. That's all.
yeah, if no, that's true. If we consider like the cosmological simulation, when a few giant galaxies start to like the merge, so a small like dwarf galaxy usually can form in this kind of scenario. They cannot form in a single, at least in our local universe that we can reach by our instrument to be able to detect the black holes using the dynamical method. But yeah, when people go toward the high redshift, they use like only X-ray emission or this kind of thing. They can probably catch those galaxies not in a complicated environment in the high redshift. But for dynamical modeling, we are only able to focus in local universe because the observational constraint, and the local universe is mainly like a complicated environment. But that's a good point.
I'm going to use my host for just to ask the question. So for NGC 4486b, do we know that it had like a tidal encounter with M87? Or like, is that the theory is that it used to be more massive and it got stripped away by M87?
Yes, yeah,
Okay.
it's clearly, this is the very high velocity dispersion. That's this mass of the tiny little object, they cannot have their own way. So it was like the massive dwarf galaxy, at least in the like high-end mass dwarf galaxy, and it's stripped away. So first of all, it's an overmassive black hole. It should be a big galaxy before, a big dwarf galaxy. No dark matter, so it's probably also at the stripped away, and also high velocity dispersion, and also very close and highly bounded to M87.
Okay.
I think they are all the narrative in the way that it is probably stripped away.
But its black hole mass is greater than that of Andromeda, so would you expect that it would be actually have more mass?
Yes.
Okay.
Yes, it was I don't say massive galaxy, but a massive dwarf galaxy, in high end of dwarf galaxy. No, Andromeda is not even a dwarf. So it's a massive D it's given, I think. But, the formation of the black hole, which is like a massive, probably it has a few more merger, during the early time that combine a few more massive black holes, and, like the history about how the black hole get fitted and like grows. But yeah, that's the point. That's, it's how massive this black hole is also related the history of the merger history. But compared to the M31, first of all, it's a massive galaxy, but it is even a dwarf galaxy, considering like the earliest, it was a massive dwarf galaxy. So that's the first difference. And then it's still the black hole is more massive than M31. And the peak in this galaxy is like 12 parsecs separated, but in M31 is around 1.8 parsec. And another things about this galaxy, the difference between this one and the M31 here, the center of the black hole is like 6 parsec away from the center of these isophotes, but in M31, the black hole is almost in the center. So there are some characteristic difference between these and M31, clearly, yeah. But considering only eccentric disk and the mass of the black hole, they have like the kind of like a scaling, because the black hole in M31 is 6 times. So the black hole in this system is 6 times more massive than the black hole is M31. And the 2-peak separation in this one is also 6 times larger than the separation peak in the M31. So in eccentric disk, I think there are something related, but the total merger, I mean, the formation history of these galaxies are totally, yeah.
So I also have a follow-up question on that. The 6 times 10 to the 8 solar mass estimate is coming from isotropic model.
No, in the Schwarzschild isotropic, we don't have we don't fix isotropic, you know.
Okay.
It's like it's axisymmetric.
Because I was thinking that maybe like if we wanted to model this with an eccentric disk, then the supermassive black hole estimate might actually change. Like, because we're specifically going to use an asymmetric.
Yes. You know, the point is in black hole, we have H4. So H4 data is basically present how anisotropy is your line of sight velocity profile. So it's so flexible to catch any kind of anisotropy, the Schwarzschild, even axisymmetric model. So it's for the internal kinematic, the Schwarzschild model is powerful to like catch any kind of, and you know, it's like it's not a constant anisotropy. It's changed with the radius. For example, in Jean's model, we need to consider one constant like anisotropy parameter for the whole system. But for the Schwarzschild model, with different radius, the orbits can have different anisotropy, right? So it's so flexible to reproduce the different kinematic with different anisotropy features.
Yeah, I should probably stop. Any more questions from the crowd? Yeah.
Are the constraints like observationally limited now or by the methodology? Because the methodology seems like almost.
You're absolutely right. So, you know, the point is many people asking, so where are intermediate mass black holes? So, you know, for example, I think there is no black hole in these low mass galaxies, or there are massive black holes. So but someone, you know, can easily pop up and ask a question how you are sure about the intermediate. There is no intermediate mass black holes. It's absolutely because of observational challenges. Because, you know, if there is an intermediate mass black holes, for example, for these systems like the UCD, the velocity dispersion is around 35 kilometers per second. With a massive black hole, consider an intermediate mass black hole, the velocity dispersion is 20 kilometers per second, far below the JWST resolution. So if only there are a few galaxies in the local group, very close to the Milky Way, they are good potential to looking at them if there is an intermediate mass black hole. But it's mostly observationally challenged. You know, if you even give us a kinematic like that for a galaxy in high redshift, we can give you some output. But yeah, it's basically mainly about the observational challenge. And you know, some, for example, dwarf galaxies in the field, they are low velocity dispersion profile. You know, they get harassed by giant galaxies. So the internal velocity dispersion is very low. And you know, like recovering the kinematics or getting a high resolution kinematic, it's really challenging.
Great. Let's thank Behzad again. And he still has a few open slots in the afternoon. Everybody should have gotten the meeting sign up sheet.